This is Algebra 2, Lesson 89 on page 368. We have more graphing on number lines, but it's going to look different now. Now we're going to have two equations. Either the equations are going to be conjunctions, which will have the word and in them, and we're always graphing the values in between two numbers when we have a conjunction. It's always in between two numbers. For a disjunction, you're going to have the word or, and our lines will always go away from one another. So this concept, you need to understand. Conjunctions, everything in between. Disjunctions, they always go away because we're going to add to this. All right, so let's look at conjunctions first. Again, it's going to tell you the domain is integers. I always graph reals. All right, so look at 89.1. It says negative x minus 3 less than or equal to negative 2. And, keyword, my brain is saying it's a conjunction. I'm going to graph between two values. And x minus 2 less than 1. I'm doing all reals. So we'll solve both equations for the value of x. We have negative x less than or equal to 1. Remember, I multiply every term by a negative. That changes the direction of the sign without losing the inequality. X becomes positive, the other one becomes negative. So I'm graphing every number above negative 1, including negative 1. We'll solve the other equation. For x, x less than 3. So we're going to go less than negative 1 all the way, greater than or equal to negative 1, all the way to 3. So negative 1, 0, 1, 2, 3. At negative 1, what type of interval do we have? Closed or open? Closed. And at 3, what do we have? Open, and it's every value in between. Okay, I want to write this as one inequality. So I'm going to combine this one with this one so you can see something. So I'm going to switch it around. Really, this is negative 1. You agree? I switched it around? Yeah. Notice the direction of the signs. Less than are conjunctions. Eventually. Okay, so you can write it this way. What does my interval notation look like?
Bracket.
Yep.
1.
Negative 1, comma. 3. Parentheses. That's interval notation. All right, let's work 89.2. Now they give it, the word and is not here, but it looks similar to this. All right, so look, we have negative 2 less than x minus 2 less than or equal to 4. When it is all in one statement, you always say it's a conjunction. So this, I could read this as two statements. Look, I take the middle and I say negative 2 less than x minus 2 and x minus 2 less than or equal to 4. Do you see the two statements? The middle goes with the left and the right, but I can work it as one inequality. As long as what I do in the middle, I do to both sides. So I'm going to add 2 in the middle to get rid of the 2. I have to add 2 over here. I have to add 2 over here. I'm left with x in the middle. That's 0. That's 6. Notice, less than, conjunction, okay? We're gonna memorize that eventually. Less than, conjunction, and everything in the middle. All right, so I'm gonna start 0, we'll do -1. 1, 2, 3, 4, 5, 6. So at 0, open or closed interval? Open at 0. 6, open or closed? Closed. And it's everything in between. Interval notation, what goes with 0? Parentheses or bracket? Parentheses, what goes with 6?
Bracket.
Got it? All right, so conjunctions and are less than in one statement. Disjunctions are or, and they end up greater than, and they go away from one another. So let's work 89.3. We have negative x greater than or equal to 3, or negative x less than -1. We're going to graph rails. Or I'm thinking disjunction. My lines are going to go away from each other. All right, so I'm going to multiply both of these by negative. The direction of the sign changes and the sign of both terms changes. I'm going to do the same thing here. I'm going to multiply both of these by negative. The direction of the sign changes. The sign of both terms changes. All right, so x is less than -3. So less than -3 is a open or closed interval. Less than or equal to? Closed, and the line goes left. Greater than 1, I have an open interval, and my line goes that direction. All right, so this piece, interval notation, is -infinity up to -3 bracket. And then we'll learn this towards the very end. It also includes these solutions. That's what this is. It's the union of both of these. Parentheses 1 all the way to positive infinity. So it is both, that U means both of those answers are solutions to this original. Okay, let's write this as 1. I'm gonna flip them. So the -3 goes here. All right, you agree? All right, so now I'm just going to put this piece, the x is already here. All right, what signs do you see? What did we see with conjunctions? With disjunctions, we see greater than, with x, when x is in the middle. And we're going to have 2 sets of solutions with disjunctions. With conjunctions, we're just going to have that one set of solutions that's in between those 2 values. So conjunctions and disjunctions are here to stay throughout this textbook. And we're going to do rational equations. All right, let's do 89.4. All right, 89.4 is -x minus 2 greater than or equal to 0, or, keyword, I'm telling myself a disjunction, they're going away from each other. X plus 3 greater than 6, we're always graphing reals. I'm going to add the 2 to both sides of the inequality, and we have -x greater than or equal to 2. Now I'm going to multiply by negative. When I multiply by negative, the signs of both of the terms change. The direction of the sign changes. I do not lose my equality. X becomes positive, 2 becomes negative. When I subtract my 3 in this other inequality, I have x greater than 3. So x is going to be less than -2 going in that direction. X is going to be greater than 3 going in this direction. Okay. I prefer you to graph these just a tad above the line, exactly like and not on the line, because I can't really tell which direction your line goes if you graph on the line. All right, so less than or equal to -2, closed interval to the left. Like if I did this, it's just harder to read. So always do it just a tad above the line. Greater than 3, open interval, and I go to the right. What does this look like in interval notation, this piece?
Negative, infinity, and then -2. With a bracket for -2. And parentheses.
Got it? Does everybody have this interval notation? What does it look like for 3? All right, somebody other than Hannah, say it. Parentheses. Not bracket. There we go. Parentheses. Always goes with infinity. If I were to put these two together, we would see the greater than signs. All right, the last part of this lesson is a review from geometry. But before we get there, I'm going to erase this. Somebody tell me what a conjunction is.
Two complete clauses.
Greater than.
Two what? What's a conjunction? Oh, you're thinking the song on, what is it called?
Oh,
Something rocks.
What's your phone?
School rock. School rock. Schoolhouse rock. Yeah. Okay, but in math, what's a conjunction?
What's
It's greater than.
greater than?
Wait, are you talking about, wait, which one did you say?
Conjunction is
Line.
less than, and it's and they both go together, right? You're graphing everything in between. A disjunction is greater than the word or, and you're going to weigh. And so you have two separate interval notations with that little union sign in between. Okay, products of chords and secants. Chords lie inside a circle. Secants are lines through a circle. Such that if I have an angle in between, what do I do to the arcs? If the angle's inside, what do I do to the arcs? Add them, divide by 2. So that's 170 divided by 2, that's the value of x. What if it's outside?
Subtract and divide by 2.
Subtract and divide by 2. What would that be? 80 over 2 would be x. All right, so that we have done some of those. Here also is chords. Anytime we have chords in a circle, I'm going to draw bigger. Okay, we're going to call that chord 1 and this one chord 2. Let's say in chord 1 we have length A and B. And in chord 2 we have length C and D. The products of the segments of the chords inscribed in a circle are equal. So A times B equals C times D. That's always true. Look at it. 2 times 6 equals 3 times 4. The products of a chord inside a circle, the products of the segments of the chords inside a circle are always, always equal. All right, so look at this one. We have 3, 7, 5, and x. I just multiply. 3 times 7 is that chord. The segments of that chord have to equal 5 times x. So 21 equals 5x. Divide by 5. X is 5 over 21. Now what happens when we have a line that goes outside the circle? It's not a chord. What happens when we have a segment? It's the outside times the whole length equals the outside times the whole length. All right, so let's do it with this one: 3, 5, 2, and 10. All right, you see the two secants? So it's the outside times the length of the whole, which is 8, equals the outside times the length of the whole, which is 12. All right. So what if I have this? It's the same. The outside, if I look, times the length of the whole, I add them. Equals, you see that? The outside times the length of the whole, and you solve. For x, you have to distribute the 4. But there's one more. What if we have a tangent line? Hang with me. It's the same rule. The outside times the length of the whole, we're adding them, equals the outside times the length of the whole line. What's the length of the whole line? That's correct. Got it? Outside times whole equals outside times whole.